Hello everyone, welcome to Chemical Engineering Knowledge. In this lecture we will discuss about the chemical reaction engineering. We will discuss about the membrane reactors. So what is membrane reactor? Nowadays it is an important technology, it is an advanced technology. People use membrane reactor instead of conventional reactors. This is because conventional reactors are thermodynamically limited and there is very little conversion in conventional reactors like PFR, PBR. So we are using membrane reactor. So it is used to increase the selectivity. One important point here is that membrane reactor is used to increase the selectivity. So selectivity is nothing but it is we select one component, we wanted to increase the conversion of one component as compared to the conversion of another component. So for example, selectivity of component C with respect to component D will be denoted as C divided by D. So the selectivity, we want to increase the conversion of one component as compared to the conversion of another component. So it is used to increase the selectivity of reaction or the selectivity of certain components which we want to is our product. The other important point here is that membrane reactor is used to increase the conversion of certain components. So it is used to increase the conversion of certain components, right? Here we will discuss. Similarly, membrane reactor are used in those places, membrane reactor are used for those reactions which are thermodynamically limited. Now what does mean by thermodynamically limited? Thermodynamically limited reaction mean that suppose we A is converted into B and B after certain B is formed, then B again be converted into A. So this is reversible reaction. So for thermodynamically limited reaction, it means that the conversion of A is very small or the reaction is more toward the left side. So left side reaction is toward the left side. This side, this is the left side, this is the right side. So the K value here is equilibrium constant value is very small. Equilibrium constant value is very small. So for these type of reaction which are thermodynamically limited are those reaction whose equilibrium constant value is very small, are those reaction whose conversion is very small. So these type of reaction are called thermodynamically limited reaction. For example, if A plus B reacted and it gives us C plus D, then A and B converted and it gives C and D. After a certain time, C and D combine and it gives us A plus B. So thermodynamically limited means that very small amount of A and B are converted into C and D. So it means that the conversion of A and B is very small. Conversion of A and conversion of B is very small. This type of reaction, the K value, equilibrium constant value is very small for this type of reaction. So we wanted to increase the conversion of A and B, and we want to reach the equilibrium earlier in very short time. So for this purpose we are using the membrane reactor. So there are various type of membrane reactors. The first type is the IMRCF. IMRCF mean the inert, I mean inert, M mean membrane, R mean reactor, and C mean catalyst pellet, and F mean fluid. So inert membrane reactor with catalyst particle on fluid side. It means inert membrane reactor with catalyst particle on fluid side. The name suggests that the catalyst here is the catalyst particle here is on the fluid side, and the membrane is inert. The membrane don't react with the reactant or product molecules. So only the membrane is used to allow certain component to pass through the membrane and to prevent other component from passing through the membrane. So very limited amount of product or very certain time of certain amount of molecule will pass through the membrane, and the membrane will be inert. Remember, the membrane will not react with the reactant or product. The membrane will only allow certain molecule to pass through it. The other type of membrane is the membrane catalytic reactor. Membrane catalytic reactor. So membrane catalytic reactor, it is that type of reactor where membrane uses a catalyst. So the reactant molecule will react with the membrane surface, and after reaction the product molecule will form. So this is the membrane catalytic reactor. Or in some cases we apply catalyst particle on the membrane surface to react with the reactant molecules. So sometimes the membrane itself acts as a catalyst. In some cases we apply certain catalyst molecule or catalyst particle on the membrane surface to react with the reactant molecule and form our product which we want in our reaction. So these are the catalyst particle. This is the catalyst particle. These are the various catalyst particle. These are the catalyst pellets. And this is the IMRCF, inert membrane reactor with catalyst pellet on feed side. So this is the feed hexane. This is the hexane, and this is the permeate, and this is the catalyst particle. These are the catalyst particle. These are the catalyst particle. These are the catalyst particle, and this is the feed. So catalyst particle is on the feed side, and the inert membrane. This is the membrane. This one. This is the membrane. This is the membrane. This is the membrane. This red one. So inert membrane. This is the inert membrane, and this is a reactor. Inert membrane reactor with catalyst particle. This is the catalyst particle, and it is on the feed side. So this is the feed, and this is our reactant, and this is our product. The product is benzene, and this is the catalyst particle. This is the inert membrane. This is the permeate side. So for example, hexane is converted into the benzene and hydrogen. So as the molecule of hydrogen is, molecular size of hydrogen is very small, so the hydrogen will pass through the membrane. This is the hydrogen will pass through the membrane. So the membrane allow only a hydrogen molecule to pass through it, because the molecule size of hydrogen is very small as compared to benzene molecule. For example, benzene molecule is this type, and hydrogen is very small. Hydrogen molecule is very small, so hydrogen will pass through the membrane, and the benzene and the hexane molecule will not pass through the membrane surface. So this is the, when hydrogen molecule pass through the membrane surface, it will enter into this space. This is the shell side. This is the tube. In the tube side there is catalyst particle, and when the hydrogen molecule pass through the membrane, this is the membrane, it will come to this shell side. So in the shell side we are using some sweep gases. So the sweep gas will remove the hydrogen from this place to the other side. Similarly, we will use some gases like nitrogen to remove hydrogen and to travel hydrogen to this side. So this sweep gas will increase the conversion, and it will increase the driving force for hydrogen, which are entering from this inner side to the outer side. So this is the inner membrane membrane reactor with catalyst particle and feed side. This is the catalytic membrane reactor, CMR, catalytic membrane reactor. This is the feed, hexane, this is the benzene, this is the membrane, and the membrane acts as a catalyst. This is the membrane, this one. It is membrane, like fluidized that type. So this one is the membrane. The surface area of this is the surface area of the membrane. This is the surface area, and this is the feed, this is the product. So this is the catalytic membrane. This membrane acts as a catalyst. This feed will react with the membrane surface, and the product will form. So and similarly, after the reaction with hydrogen, the hydrogen which are formed, that will pass through the membrane also. After the reaction, the hydrogen will be, after the reaction, the hydrogen are passing through this membrane. So this is the membrane catalytic reactor. Membrane catalytic reactor. So here the membrane is made of catalyst. Membrane surface area is made of catalyst. But here the membrane surface area is not made of catalyst, but catalyst particles are present inside the membrane. Remember, this is the difference. Now, this is the cross-sectional area of membrane. This is the cross-sectional area of membrane. This membrane can be made of ceramic. These are ceramic particles. This can be also made of ceramic and with catalyst particle on the surface. So this is the cross-sectional area. A, B, and C enter into the membrane, and this is the particle of catalyst particle. The cross-sectional area of this membrane. The A, B, and C are the product, and this is volume. A, B, and C are entry at volume V. A, B, and C are leaving at volume V plus delta V, and the component V leaving through the side of the membrane, which is the RD. So the rate of diffusion out of component D through the side of the membrane is denoted by RD. Now, in membrane reactor we will use the volume of reactor, not the weight of catalyst. So we will use the volume of the reactor instead of the weight of catalyst. So the relation between weight and volume is nothing but it is by volume and weight are related by the density of the catalyst. So the bulk density of the catalyst particle is rho B. So weight of catalyst is equal to density into volume of reactor. So we will use the volume of reactor, not the weight of catalyst. So the volume and weight relation are, this is the weight of catalyst in the kilogram, and the density of catalyst is kilogram per cubic meter of catalyst, and the volume of catalyst is cubic meter. So this is the relationship between volume and weight of catalyst. So again, this is a membrane reactor. A is entering, B and C leaving the reactor. It is something like this. A gives us B plus C, and equilibrium. After equilibrium, we want to increase the conversion of B, so the B will sweep out through the side of the membrane. In order to increase the conversion of component, in order to increase the conversion of component A, in order to shift the equilibrium toward the left side, as we have discussed the Le Chatelier's principle for the reversible reaction. So what will be the mole balance on component A? What will be the mole balance on component A? So we are taking some small cross-sectional area of this reactor. So this is the cross-sectional area, small cross-sectional area of this blue reactor. So the mole balance on component A is molar flow rate of component A at the volume V. So this is V, and this is V plus delta V. So molar flow rate of component A at the volume V is Fa at V, and the molar flow rate of component A at volume V plus delta V is Fa into V plus delta V. So entering, this is A enter, A leaving, and this delta V is the volume of the small volume of the reactor is delta V. This one, delta V. So again, write the mole balance. Mole balance is nothing but it is input minus output plus generation is equal to accumulation. So inlet of component A is Fa. This is the input minus output plus generation, the rate of conversion of component A, and this is the small volume delta V. And it is mole of component A changes with the passage of time. So at steady state, the component A will be not changes with the passage of time. So at steady state the term will be 0. So inlet minus output plus generation is equal to 0. Again rearrange this equation. Fa at V plus delta V minus Fa at V is equal to Ra into V. Again we have written this Fa V plus delta V minus Fa at V is equal to Ra and delta V. So divide this equation by delta V. So delta V is cancelled with delta V, and here delta V occur. Again delta V approaches to 0, then this equation will be approaches to dFA divided by dV is equal to Ra using the first derivative principle, like Fa f at x plus delta x minus f of x divided by delta x is equal to, when delta x tends to 0, then this term will be equal to dFA divided by dx, which is nothing but they are the first order derivative. So mole balance on component B. So the mole balance on component A is, we get this equation, dFA divided by dV is equal to RA. Similarly, the mole balance on component B is, this is A is entering, here B is producing, in this place B is also producing. So B, if we take this small volume, so here B is entering because B is produced in this place. So B is entering, B leaving, but B also diffuses through the side of the membrane. The membrane is semi-permeable membrane, so the membrane only allows certain component to pass through it, but it not allow other component like A and C, because the molecular size of A and C are very large as compared to the molecular size of B. So B is diffusing out through the membrane. So here the mole balance on component B is entering. You take this small cross-sectional area, this small cross-sectional area of the reactor. So here B is entering at this V position, B leaving at V plus delta V, but B also diffuses out through the semi-permeable membrane. This is the semi-permeable membrane which only allow component B. So again, write the mole balance on component B, input minus output plus generation is equal to accumulation. So B is entering at V position, B is leaving at V plus delta V position, but B is also leaving through the side of the membrane by diffusion. So out by B outing by diffusion, plus generation of B, which is RB into delta V, and accumulation. So its steady state accumulation term will be 0. The inlet B, outlet of B, diffusing out of B by using the Fick's law. By using Fick's law of molecular diffusion, so B is diffusing out through the sides of the membrane like this. This is the membrane, this one. And B here, B is produced, but B is diffusing out through the sides of the membrane due to the concentration gradient. So dCB divided by dZ. Suppose this is the Z direction. So dCB divided by dZ is nothing but the molar flux of component B using the Fick's law of molecular diffusion. If you don't know Fick's law, the link will be given in the description. I will give you link in the description. Watch video about the Fick's law. You will fully understand the Fick's law of molecular diffusion. So this is B is diffusing out, and the rate of generation of component B, and this steady state, this term will be 0, accumulation term. Now this is the inlet, B is entering, B leaving, B is diffusing out through the side of the membrane. The rate of generation of component B, and this is its steady state, the accumulation term is 0. Now what is diffusing out? Diffusing out term means that the molar flow rate of component B, which are diffusing out through unit volume of the reactor. So the molar flow rate of component B, passing through unit volume of the reactor. So suppose this is the unit volume of the reactor, and this is the component B, which are passing through the mole of component B. The mole of component B is passing through this unit volume of the reactor. So mole it is denoted by RB, rate of diffusing out of component B. The rate of diffusing of component B through the side of the membrane will be denoted by RB. The rate of diffusing out of component B through the side of the membrane will be denoted by RB. And it is nothing but the mole of component B, this mole of component B, which are diffusing out through this volume of the reactor in unit time. So mole of B diffusing per unit time through unit volume of the reactor, mole per unit volume into time. The unit is mole per unit time into, this is rate, RB, R capital RB. So rate of removal of component B by diffusion is RB. So mole of B per unit volume per unit time, RB is mole per unit volume per unit time. So RB will multiply the volume of reactor. This will multiply volume. We will give the mole of component B, which mole of component B which passes through the sides of the membrane reactor in unit time, which is given by FB. Now this is the inlet outlet plus the diffusing out, mole of B diffusing out to the side of the membrane, like this one. This is FB. So the side of the membrane, and again this is the rate of generation term. So again rearrange this equation. FB out minus input, the rate of generation diffusing out, divided this whole equation by delta V. So we divide by delta V and let delta V 20, then we will get this equation. So delta V 20, then FB divided by dV will be equal to RB minus the rate of conversion of component B, the rate of appearance of component B minus the rate of disappearance of component B by using diffusion law, by diffusing through the side of the membrane, minus capital RP. As we know that R minus RA is equal to KCA, we all do know from rate law. So this is also a rate term that will be equal to Km to Cv, change in concentration of B. RB will be equal to change in concentration of B, mean the concentration of component B inside the membrane, like this. If B is produced, so the concentration of B inside the membrane will be high, and this is the outlet of the membrane, so the concentration of B outside the membrane will be very small because of sweet gases. Due to sweet gases, the concentration of B here will be 0, outside will be 0 or very small. So outside the concentration of component B, we ignore it, negligible, because due to sweet gases the concentration to this in this side will be very small. So the concentration of component B inside the membrane, this side, this one, and this is the K, the mass transfer coefficient. So the mass transfer coefficient. So mole balance on component C is similar to component B, like the same process. Component C entering outlet generation, its steady state will be 0. Rearrange this equation. So mole balance on component C will be dFc divided by d is equal to RC. Again, this is the rate of the mole per unit volume per unit time outing through the sides of the membrane will be equal to the mass transfer coefficient and to change in concentration of B. And we also discussed that the change in concentration of B means the mole concentration of component B here and concentration of B in the sweet gases, like this one, like this one. Concentration of B here is, suppose the concentration of B here is, concentration of hydrogen in this place will be this one, suppose this, and the concentration of hydrogen in the sweet gas in this place is very small, like in this place concentration here is very small because of sweet gases. So this is the concentration difference. So this is the mass transfer coefficient. Okay, is the mass transfer coefficient. Mass transfer coefficient. The unit is meter per second. Its unit changes on the basis of driving force. The driving force can be partial pressure difference, it can be concentration gradient. So similarly, we know from the convective molar flux, we can the convective molar flux can be denoted by Na. Suppose A is transferring from one place to another place by convection process. In the mass transfer, then molar flux of component A will be equal to K into change in concentration of component A. So the molar flux of component A mean mole per unit time per unit area, mole per unit time per unit area. Because flux is nothing but mole per unit area per unit time, molar flux. So the RA mean value will be equal to mole of A. The RA value will be equal to the mole per unit area per unit time, and we multiply it by the specific surface area, which is nothing but denoted by A, and its unit is square meter per unit volume. So this will cancel with this. Again, it is mole per unit volume per unit time. So we know that the mole per unit volume per unit time is nothing but the molar flux of component A. For example, for molar flux of component A, they are multiplied by specific surface area. Similarly, this is for the component A. So the molar flow rate, the molar rate of component B, which is diffusing out the side of membrane, will be included by RB, and it will be nothing but the molar flux of component B, which is leaving. Suppose this is the side of the membrane, and the flux of component B, due to the concentration gradient, the flux of component B through this side of the membrane will be NB, and the specific surface area will be denoted by A, and the unit is meter square per cubic meter, and this is the mole per unit volume of the reactor per unit time. So again this cancel with mole per unit area. So again this cancel with this, and this is the mole per unit time per unit area. This one. So this is the relation between the RB and the NB. So this was just introduction to the membrane reactor. In the coming lecture we will use polymer. Software to solve the reversible reaction in the membrane reactor. A real world problem. We will solve a real world problem about the reversible reaction in membrane reactor using polymer. Thank you very much for your attention. If you are new to the channel, please like and subscribe. Thank you very much.